Common graphs and misleading statistics. This video will help you create circle, bar, and line graphs, and also identify misleading graphs and statistics. Create circle, bar, and line graphs. Graphs are used to display data in a form that is easy to understand. Newspapers, magazines, and television shows often use graphs to represent data because it gives the reader or viewer a lot of information at a quick glance. Circle graphs are often used to give a visual representation of the different parts of a whole. So when we're comparing parts of a whole in terms of like a population demographic or any other situation where we're comparing and seeing kind of the breakdown of all the different parts that make up this whole thing, oftentimes we'll use a circle graph. Okay? Let's take a look at a definition here. A circle graph is a circular graph divided into pie-shaped pieces, and we call those pieces sectors, where each sector represents one part of the data set. The entire circle represents the whole, or 100% of the data. So you can see I just made a quick circle graph here based on sales, let's say, and then first quarter sales, which represented the most, which was 65%. And notice the sector that 65% represents is actually, in fact, 65% of the circle. And then second quarter, 25%, fourth quarter, 10%. So it's important in a circle graph to get these sectors the exact size of the percentage. So that way, when I look at this graph, I can see, oh yeah, there's the percentage, but I also get a visual of how much that is in terms of the whole. Okay, let's take a look at a practice problem here. Students were polled at Kellogg Community College to get information about their intended major. Create a circle graph from the following survey numbers. So we've got 2,675 of the students were in an allied health program, 1,900 were in a transfer program, 800 in manufacturing, and 500 in computer technology. So what we're going to do is we are going to take this information and we are going to turn this into a circle graph here. So let's talk about a couple of details before we start that. So the first thing we want to do is we want to calculate a percentage here for each of these. And remember, when we're looking at a percentage, kind of in its basic form, we're going to take the part that we're talking about divided by the whole, and that will give us our percent here. Now, notice we've given you the numbers for all the parts, but we've not given you the number for the whole. So you're going to have to add these all up to get the whole or total population in order to calculate these percentages. Once we get the percentages, then we take and we multiply the percentages times 360 degrees. The reason we're doing that is because the whole entire circle is 360 degrees. If we take this percent of 360 degrees, it will tell us then the degrees that that our sector needs to occupy on that circle. So once we multiply the percent times 360, it will give us an angle measure for each of these sectors. Then we're going to use our protractor to draw and measure out, the angle measures in each sector to create the pie graph. Now, I also included another video in this assignment that shows you basically how to construct a pie graph using the protractor. So make sure you've watched that video if you need help with that. And then the last thing we're going to do here is we are going to color each sector and make a legend, just like I did up here in this sales picture here, so that when somebody looks at our graph, sorry, going the wrong way there. When somebody looks at our graph, they can quickly get the information. Notice first quarter was blue. We've got a little legend here, so we can look right there. So you want to make a little legend, and you want to color coordinate it on your circle graph. All right, let's go ahead now and pause your video player now and answer all these parts to create your circle graph. When you're done, hit play to see how you did. Okay. So let's take a look at some answers here. So our whole in this case, when I added all of these up, was 5,875 total students. And so you notice as I go to calculate each of these percentages here, I'm taking the part that we're talking about divided by the whole thing, which is the 5,875. When I went through and calculated these, I got 8.5% for computer tech, 45.5% for allied health, 13.6% for manufacturing, and 32.3% for transfer. Now, if you rounded these to a nearest percentage, that's fine. Like, for example, you could have written computer tech was 9% and allied health was 46%. That would have been fine. So then what I do in part B is I take each of these percentages and I multiply times the whole thing, which is the circle here, 360 degrees, to find out the angle measure for each of these pi sectors. And so you can see here, computer tech, we got 31 degrees, allied health was 164 degrees, manufacturing 49 degrees, and transfer 116 degrees. Then I came down for my pie chart here, and the first thing I did is I started with a line, initial line. I found the center of the circle, drew a line, and that line could start anywhere. It doesn't matter where that starts. And then I used my protractor to measure around. The first one was the degrees that I had listed up here before. I think that first one was 31 degrees. So I went ahead and followed those degrees, went around and drew the line, measured the next one, which I think was 146 degrees, went all the way around the circle and got each of those pi sectors labeled correctly. Then I wanted to create a legend, so you'll notice I used some colors here. Computer tech was blue, allied health was orange, manufacturing red, and transfer was gray. And I colored in all of those different sectors so that people could follow that. So hopefully you came up with a graph similar to this one. Okay, next we'll talk about bar graphs. Bar graphs are used when comparing different groups or to track changes over larger periods of time. So a little different than the circle graph. That was kind of the breakdown of the population that we were looking at. Now with bar graphs, we're used to compare things, compare different events. And so I made another simple bar graph down here. So a bar graph is a collection of rectangles that represent the different quantities in a set of data. And bar graphs are really useful for comparison. So notice this is a horizontal bar graph. A lot of times you'll see vertical bar graphs like this. In fact, in the practice problem down here, I'm going to have you create a vertical bar graph. So what we do is we create a bar for each of these, and then it's really easy to make a comparison between, in this case, again, I made something real generic here just with quarters so that we could see those. Okay, let's take a look at a practice question here. The average salary of practicing nurses by state is as follows. Mississippi, $55,710. Rhode Island, $72,720. Massachusetts, $86,810. California, $90,860. Hawaii, $83,950. And you can see we've sourced this. Just didn't make these numbers up. This came from the Bureau of Labor and Statistics. So what we're going to do here is we're going to create a bar graph to represent this data. So decide whether you want to make a horizontal or vertical bar graph. Since we had a horizontal one in the example up there, let's make a vertical bar graph, meaning that our bars are going to start at the bottom and kind of travel up each of these bars for the different salaries. Decide how you're going to label the graph. Notice I've given you some tick marks down here on the graph, but we have to decide how we're going to label those. In this case, the hard thing to decide, or the thing that's most important to decide, is how much money each of these will represent. You know, we want each of these movements to represent the same amount of money. So that way when we make our bar graph, it will be honest and accurate. So you want to figure out how much you want each of these to be in terms of the money. We're going to put the states down at the bottom of our bar graph. The reason we do that is because the states are the independent variable. The amount of money is the dependent variable. So independent means the idea or thing that can stand alone. In this case, it's the states that the practicing nurses are working in. And the states stand independently by themselves. Now, what is dependent on the state is that in certain states, you're going to make more money. In other states, you're going to make less money based on cost of living. So what we would say here is that the amount of money you make as a practicing nurse depends on the state that you're working in. And so whenever we're creating a vertical graph, either bar graph or in a little bit where we're creating a line graph, we always put our independent variable on the bottom. And our dependent variable on the side here. So this one always depends on this one down here. So something to keep track of here as we're making these graphs. So go ahead now and pause your video player, and we're going to make a bar graph for the average salaries of practicing nurses based on their states. When you're done, hit play to see how you did. So here was the graph that I made, and I noticed when I was reading it there that I missed out on Hawaii. I missed that piece of data, so let me put that Hawaii in there right now. Hawaii was a little less than California at about 84,000. So let's look at my graph here. What I decided was that each of these tick marks was going to be $10,000. That way I could start at lowest and then go all the way up and cover the highest salary, which was about $90-some thousand. So let me also add Hawaii in here. Okay, and Hawaii we said was just about $90,000. So I would put that right there. Okay, so let's see what else I did. Notice I labeled the states down below the bar graph. That's a way to do it. It would have been fine to make different colors here and create a legend off of the side, with little boxes that tell us what each of the bar graphs represent. That would have been a fine way to do it. If we do that with the little colors and legends, you want these to follow suit with your bars down here. So notice I listed Mississippi, Rhode Island, Massachusetts. I would want my legend to read the same way and in the same order. That makes it clearer for the reader. So this would have been Mississippi, Rhode Island, Massachusetts, and so on and so forth there. One thing that we don't want to do is we don't want to create a compressed graph. We wouldn't want to say that we're going to start out here at $50,000 and then each of these tick marks is going to represent an amount of money. If we cut off any part of this graph here, it's misleading. Actually, our graphs will become misleading, and it's actually, in fact, a very standard way to kind of create misleading graphs and statistical reports. We're going to talk about that in just a second, but you do want to make sure that you always start here at 0 and work yourself up by a standard increment here, a consistent increment, or else your graph will be misleading. Okay, let's talk about line graphs. Line graphs are used to track changes or show a trend over a period of time. Let's take a look at a definition now. A line graph displays data points that are connected by a line to show a trend. And so you can see I've got a triple line graph here. Notice one blue line graph, one red, one green. And we've got a legend up here. This is trends, this is flavor, and this is series 3. I guess these are 3 design companies that I've kind of made up here. And so here are my data points. In June, this one was just under 5, and it drops down here and then goes up. So I have 4 data points here. And then what we do to make our line graph is we connect those points with a line. And usually, almost always, line graphs are based on time, because we usually look at line graphs to show a trend over time. Now, in terms of, like I talked about last time, with independent and dependent variables, well, time is the ultimate independent variable, because time marches on regardless of anything else. So time here is my independent variable, and in this case, whatever I have listed over here, I just made this graph up quickly. I'm not sure what these were supposed to represent, but these values depend on the month of the year. So this is the dependent variable, this is the independent variable down here. And a lot of times we'll have more than one line graph. You can have just one line graph to talk about a trend over time, but if I use 2 or 3, then I can make a comparison of, in this case, 3 different design companies over, looks like the summertime here. Okay, let's take a look at a practice question now. The Pew Research Center investigated the median annual earnings for full-time workers aged 25 to 35 and compared these earnings by generation. And so we've got 2 sets of data they've given us here. One is that it's high school graduate salaries, and notice here they've adjusted all of these salaries to $2012. So if we look at the money in 1965, these people were not really making $31,000 a year there in salary, but we've adjusted this number so that it's to $2012. The other information here I've got college graduates, and again adjusted to $2012. So what we're going to do in this practice problem is we are going to create a double bar graph, and we're going to compare with a double bar graph over time high school graduate salaries compared to college graduate salaries. Now, the graph on the next page is all going to be blank, so you're going to have to decide what is your independent variable. You want that to go on the bottom. The dependent, you want that to go on the side. And we've got to span a couple different things. We're going to have to span these salaries. So it looks like high schools are starting maybe at 31. Oh, sorry, the high schools are starting at 27 and spanning all the way up to 32. College looks like is going to be our maximum here. It looks like our maximum is going to be about $45,000. So we want to make sure in your graph we can cover between 31,384 and then our maximum 45,500. When we do this, we want to make sure we start our graph at 0 and then work our way all the way up from 0 up to this highest level, a level that will cover this $45,000. In terms of our timeline, we are probably going to start our timeline not at 0, but we'll probably start our timeline around 1965 or maybe 1960 or something like that. And we want to make sure that our timeline covers up to 2013. So go ahead and pause your video player now, and on the next page you'll see the blank graph to work this all out. You might want to take a picture. This would be a good idea to take a picture of this data here with your phone. Here, I'll give you a little camera icon. Take a picture of that guy so that you're not flipping back and forth between trying to find the data piece and then putting it on the graph. If you take a picture of that with your phone, you can just look at your phone and have the data right there in front of you while you're trying to make this graph. Okay, let's take a look at my graph here. So I wanted to span again between 0, and I had to cover up to $45,000. It looks like my graph worked out to be up to $60,000. What I did is I made every one of these little tick marks worth $1,000. So you notice if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, $10,000, and then I just counted up that way to cover $60,000. Here, I think I made every one of these a year. So let's see, I started right here at 1965 for my first data point. And I go 66, 67, 68, 69, 70, 71, 72, 73, 74, 5. Right there, yep, that's what I did. So I counted every one of these tick marks as a year down here, and that made a nice spread for my graph. Notice independent variable here is time. Dependent variable is money, because the amount of money either a high school graduate or a college graduate is making, even in adjusted dollars values, is still going to depend on the time in which they were working. So independent, dependent, it looks like I did a blue graph for the high school graduates' salaries, and then what I did is I went through on my graph, and in 1965, the silent generation, put a point here in 1979, I think was my next data point, 1985, and then I went ahead and put the college graduates up here as well. Connected them all with straight lines. I made a little legend so that if somebody's looking at my graph here, they can see that this is the high school salaries adjusted to $2012 and college salaries adjusted to $2012. I would want to make sure I have this adjusted salary information on my graph, or else somebody might look at my graph and go, my gosh, they made that much money in 1965? That's crazy. Well, no, they didn't. But if we don't include this, somebody reading my graph would not know that. Okay, I talked about this a little bit before, but misleading graphs and statistics. This is something that happens all the time, and I think once we kind of look at a few of these graphs and learn about ways in which people use graphs and statistics to present misleading information, you'll find this stuff happening all over in your life. So this is an important concept just so you can try to look through the BS and see what the truth is here. So, misleading graphs and statistics. It's often stated that numbers don't lie. While this statement may sound profound and powerful, the numbers will only reflect reality if the data has been properly collected and presented. Data collection and presentation is routinely manipulated to inaccurately present opinions and one-sided stories. So let's take a look at a couple questions now. I'll show you what I'm talking about here. So we're going to identify the misleading information or presentation, data presentation in each of these graphs. So we want to make sure we're answering these in complete and full sentences, communicating our thinking. So here we go. take a look at our first graph here, and it says 50% of graphic designers have red hair. This is their data that they've presented to us. And so let's think about that. Look at the information on this chart here and see what is misleading. You think this is misleading in this graph. Well, if you came up with this, that the survey size was 2 designers, so if they've only surveyed 2 people, one of them had red hair, is what happened here, and so then they throw out this statistic. It's true based on their study, but it's misleading because they didn't have enough people in their sample size here. Whenever we're doing a statistical investigation, oftentimes we won't survey every single person in the population that we're talking about. We only survey a percentage of the people in the population. One thing that's really common about surveys is presidential polls and elections. I've never been called to ask for who I was going to vote for the presidential election, and most likely you have not either. But what they do is they go through and they just sample a certain amount of people. Well, the accuracy of the poll or the survey is only as accurate as how good they do a sample size. They want to make sure that that sample represents, in this case, if it's a presidential election, represents everybody in the United States. So they have to choose their sample carefully. But choosing a sample size of 2, you're not getting an accurate survey here. They're intentionally trying to mislead us because they've kept the sample size real small, or oftentimes they'll manipulate the sample size to represent one opinion or one thing. Okay, let's take a look at this next graph here. So this is about the 2008 housing crash here. And so the graph here is claiming that did AVAs cause the housing bubble burst of 2008? And so you can see the graph here, this yellow part is the home price index. And so we're starting out here in 1991 with a home price index, and you can see home prices climbing, and then they go down drastically. You can see here the babies with name Ava in 1991 started out real low, and they climbed right up here until 2008, and then they also declined. So this graph and this theory is that when people stopped naming their kids Ava, then the value of homes went significantly down. So take a moment, think about why that is misleading or what's wrong with that presentation. Okay, well hopefully you came up with this idea. Maybe not with the technical terms I'm going to use here, but when 2 graphs move together, this one climbing up and then coming down, and this one again doing the same thing, that's called correlation, basically based on correlation. So it's correlation. These graphs have a strong correlation between each other. But just because things have a strong correlation does not necessarily mean that one causes the other. So in a statistical argument here, we would say correlation does not indicate causation. It's just total coincidence here that the babies named Ava dropped off at the same time housing prices dropped off. And we can't claim that because people stopped naming their kids Ava that the housing prices went down. All right, let's take a look at some more. USDA hog wild for conferences. So here we are in 2008, we've got 2.5 million. This is the money that the Department of Agriculture spent on conferences. 2009, 14 million, 17.5 million, and then it dropped off in 2011. And this is from USA Today. They like to use these. These are called pictographs. And so there is things misleading about a pictograph. So go ahead and think about this for a second. Compare the numbers here versus the pictures. That's the information you're going to want to look at closely here. So hopefully you notice that in 2010, they've made this hog gigantic, right? But if we look at the difference in numbers, this is 14 million. This is only 3.5 more million, right? So this is not double the amount. But if you look at the picture here, the picture of this hog here looks twice as large as this one. And this happens a lot in pictographs because not only are they extending the height of the graph up a little bit, they're also extending the width. And we're kind of trained to equate area of this piece in the graph with what its actual value represents. And that's not the case here. So most of the time when you see a pictograph, the graph is going to be presented, or the data is going to be presented in a misleading fashion. Let's go ahead now and take a look at that one. I won't say a whole lot about this. Just take a look at that and see what you can see that's misleading there. Well, this one was just ridiculous, but this really was something I found for real. And you can see that U.S. Airways is talking about how much on time they are here, and they're saying, okay, we're 91% on time, and Delta, boy, they're just not doing as well. They're 91% on time. I don't know how they made that graph or got away with that, but they just did it. Amtrak train, let's see, this is evenly spaced, I guess, so we haven't misled us that way in terms of being on time, but that was a big one, 91% versus 91%, but one bar graph is longer than the other. Okay, question 5. We're going to identify the misleading graph or information here. This one is tricky, but once I show you this, you're going to see this all the time. This is the go-to way to create misleading statistics right here. Is create a bar graph or a line graph and do this trick here, and it makes it look really ridiculously larger. Like if I compare 1998 versus 2012, the numbers versus the graph don't match up. The question here is why, or how are they doing this? So go ahead and take a look at that and see if you can figure out how it is that they're making this thing look so misleading. Okay, well, hopefully you came up with this. This is kind of tricky to see at first, like I said, but once you see it once and I show you this, you'll understand. So remember when we were making our graphs above and I said that we had to start at 0, because if we don't start at 0, it makes the graphs misleading. So you can see the temperature difference here, 54.32, our average overall global temperature, versus 55.3. That is less than 1 degree difference in temperature, but this bar graph looks almost twice as big as this one. And so here's what they're doing. It's called a compressed graph. They're not starting at 0 here. They're starting at 53 degrees. So if we took this graph and looked at it starting at 0, you know, our graph might look like this, you know, with these little increments of change here. And then this one would be just a tiny little bit bigger. So this would be the 2012 year right here. And if we started at 0 down here, the difference would be minuscule, would be very minor. But what happens is if you take the graph and you just cut off the very tippy top of the graph and don't start at 0, in this case they're starting at 53 degrees, then what it does is it makes these differences between the temperatures look drastically different than they actually are. So not starting at 0 is called a compressed graph, and compressed graphs are everywhere. Just look, I'm sure you could look just every day, every single day, you could look at the newspaper or on the television when they present graphs and things, and you'll see a ton of these compressed graphs used to mislead things. All right, let's take a look at this. This was about a presidential election. Again, this was the Republican nominations. So go ahead and take a look at that and see what you can find misleading about that one. Well, so these are GOP candidates for the 2012 presidential election, and you can see that the candidates here prefer Palin. They 70% there, Romney 60%, Huckabee 63%. So Romney has actually the smallest backing of candidates, but his pie piece looks the largest. So whoever is presenting this information, it's like some Fox channel here is presenting this information. So they've created the pie chart not accurate. And the way they do that is instead of making the pie chart 2-dimensional, they make the pie chart 3-dimensional. And then when you kind of make it 3-dimensional, you can see how it's kind of rotated back there. Then the pie pieces in the front look bigger than the pie pieces in the back because they've tilted it in 3D. And they've put that piece in the front kind of facing forward to make it look larger. So anytime you see a circle graph that has been tilted and they're giving you a 3D vision of it, there's no longer presenting accurately the correct size of the sectors of that circle graph. And that's what they've done here with this one, is they've tilted that pie graph. So anytime you see a tilted pie graph, somebody's trying to mislead you with statistics. Okay, let's Let's take a look at this one here. See what you can find. So Southwest border apprehensions. And we're given 2011, 2012, 2013. You can see 2013 looks quite a bit bigger when we look at the numbers, 170,000 versus 192,000. It is 22,000, but it looks almost twice as much. And the way they're doing this, again, is a compressed graph. You see, they're starting over here at 155,000, not at 0. So they're trying to mislead us here with Southwest border apprehensions. Okay. So let me tell you about this, what this means in terms of creating graphs. Extrapolation is we take a look at a set of data, we look at the trend or pattern in that data, and then we extend that trend or pattern outside of the data set. So in this case, this person is saying, yesterday you had 0 wives, today you have 1 wife. We're going to create a trend line here based on those 2 data points. And you can see, as a result, by next month you'll have over 4 dozen husbands. Better get a bulk rate on wedding cake. So I guess the thing here is that we can't extrapolate with data unless we have enough data points. So it's really important before we start to extrapolate and predict what's going to happen in the future that we're predicting what's going to happen with enough data points. If we had gone one more day here in their data set, it would have said 0 husbands that day, married 1 husband today, 0 husbands the next day. Then our graph might have been a little more accurate in terms of extrapolation. So again, it's very similar to sample size. If we aren't getting enough data in here, we can't make predictions about what's going to happen in the future, at least not accurately. Okay, let's take a look at this one now. Over 2 million Americans exposed to drinking water this year will die. Well, hopefully you came up with this. Correlation does not equal causation. So this year, unfortunately, 2 million Americans probably will die. But they're not going to die from drinking water. They're going to die from all sorts of things. It's possible that maybe a small percentage or small number of those people could have been exposed to some bad drinking water and died. But again, one does not cause the next. Most people will have drinking water in their lives. We're all drinking water all the time. But it doesn't mean that that's what's causing these deaths. There's all kinds of other things. So again, you want to watch for a correlation and causation. There has to be some reason to believe this piece of information. There has to be some cause to believe it. If they're unrelated, then somebody's trying to mislead you. All right, let's take a look at this one here. Colgate Sensitive Pro Relief. 9 out of 10 dentists who tried it would recommend it. See what you can think about that one, what might be wrong there, misleading. Well, so here it is right here. And that's our sample size. So they have surveyed 77 dentists to make this claim about Colgate Pro Relief. Well, there's a lot of dentists. And I don't even know if they're talking about just dentists in the United States here. They might be talking about dentists of the world. And if we're talking about dentists of the world, then 77 is a tiny little sample size. It's weird, too, with 77 being the sample size, coming up with a number of 9 out of 10. It would be really hard to come up, in fact, impossible to come up with this 9 out of 10. You would have 9 point something maybe, or 8 point something. Now they've rounded these numbers. Clearly, they've rounded those numbers to make the advertisement more simple. Federal welfare received in the U.S. Let's take a look at this one and see what you think. Well, hopefully you caught on again. This is another compressed graph. We're starting at 94 million, not at 0. So it's making things look like they're growing like crazy when in fact this is a pretty steady increase there. But not as much as they're trying to make it look. All right, one last one here. Millions of toys sold. Well, hopefully you saw this was a pictograph. So going from 200 to 300 is a jump, but it's not more than twice. The area of this horse here is more than twice the area of that. So this pictograph is misleading us.